We think of the laws of physics as these unbreakable rules, right? Set in stone. But what if I told you that one of the most important set of laws, the ones that run everything from a bolt of lightning to the screen you're staring at right now, wasn't so rigid? What if it had this secret flexibility, this kind of wiggle room that physicists use all the time?
And listen, this isn't just some abstract idea. This hidden flexibility is a real thing, a tool they actually use. It's not a mistake in the math, it's an incredibly powerful feature. It's the key to solving some of the hardest problems out there. So that's the big question, isn't it? Where does this freedom come from? And what does it really tell us about how the universe works? Okay, so it all starts right here. With these four, well, they're elegant, but let's be honest, they look a little intimidating. These are Maxwell's equations, and they are the absolute bedrock of what we're talking about today. You've got the electric field, E, and the magnetic field, B. And these equations describe how they're connected, how they're created by charges and currents, and how they affect each other. This is pretty much the entire rulebook for electricity, magnetism, and even light. But here's the catch. See, these equations are what we call coupled. What that means is a changing magnetic field makes an electric field, and you guessed it, a changing electric field makes a magnetic one. They're stuck in this endless feedback loop, so you can't really solve for one without already knowing what the other is doing. It's a real mathematical headache, a knot we've got to figure out how to untangle.
So, how in the world do you untie a knot like that? Well, physicists came up with a really clever strategy. Instead of trying to wrestle with the electric and magnetic fields directly, they brought in a couple of mathematical sidekicks. They're called potentials, and their whole job is to make this problem way easier to handle. All right, first up, we've got something called the vector potential. We just call it A. Now, here's the weird part. You can't actually go out and measure A with any instrument. It's not physical in that sense. The best way to think about it is like scaffolding on a building. It's a temporary structure we put up to help us figure out the real thing we care about, which is the magnetic field.
So why does this even work? Well, it all hinges on a key detail from Maxwell's equations themselves. It turns out the divergence of the magnetic field is always zero. What does that mean? Just imagine a river with no springs where water comes from and no drains where it goes down. The water just flows in loops. And a really cool rule in calculus says that any field that behaves like that can always be written as the curl, or you can think of it as the rotation, of some other field. So if we just define our magnetic field B to be the curl of our potential A, bam, we've automatically satisfied one of Maxwell's four equations. Just like that. One down, three to go. Our other helper is the scalar potential, which we call phi. And this one might actually sound familiar. If you've ever worked with a battery or thought about voltage, you already know what this is. It's basically the same idea. It just gives you a simple number, a potential, for every single point in space. And that helps us map out the electric field.
Okay, now we put them both together. We take our scalar potential, phi, and our vector potential, A, and use them in combination to build a full description of the electric field, E. And get this, by defining our fields this way, we've now knocked out two of Maxwell's four equations. They're just automatically satisfied. That is a massive simplification. But in solving this one problem, we've stumbled upon something, well, something really weird. You see, it turns out that our mathematical scaffolding, it's not the only one we could have built. In fact, there are tons of different ways to combine A and phi that all give you the exact same physical electric and magnetic fields. It's like there are multiple blueprints for the same building. This creates this really strange freedom, this ambiguity in how we describe things. And this right here, this is the math behind that freedom. We can take our original potentials, A and phi, and we can change them. We can literally pick any mathematical function we can dream up, we'll call it chi, and use it to tweak our potentials according to these rules on the screen. This whole process of tweaking them has a name. It's called a gauge transformation. So this is the big question, right? The million-dollar question. We just went and messed with our mathematical setup. We changed the potentials. Did we just break physics? Did we actually change the real physical fields that you could go out and measure in a lab? All right, let's check the magnetic field first. We'll calculate the new field, let's call it B prime, by taking the curl of our new potential, A prime. And when you do the math, something amazing happens. That extra bit we added, thanks to a neat little identity in vector calculus, it just vanishes. It goes to zero. Poof! The result? The new magnetic field is exactly the same as the old one. Nothing changed.
at all. Okay, fine. But what about the electric field? Let's do this same thing. We calculate E prime using our new tweaked potentials, and incredibly, the exact same thing happens. It's like a magic trick. The extra terms that we added from our transformation cancel each other out perfectly. The new electric field is identical to the old one. The physics is completely untouched.
I mean, just let that sink in for a second. We can change our underlying math in an infinite number of ways. We can pick any function chi that we want, and the actual physical reality, the fields and forces you'd measure in an experiment, stays exactly the same. This idea is called gauge invariance, and honestly, it's one of the deepest, most important concepts in all of modern physics.
So you might be thinking, okay, that's a weird mathematical party trick, but so what? Well, it's not a trick. This freedom, this isn't a bug. It's a feature, a really, really useful one. Since we have this infinite menu of mathematical descriptions to choose from, we can be picky. We can intentionally choose the one that's going to make our lives and our calculations a whole lot easier. And here's how we actually do that. We add an extra rule. We impose a condition that our potentials have to obey. This is what's known as choosing a gauge or gauge fixing. And because we know the final physics is going to be the same no matter what, we can pick a rule that's custom-built to just blow away the complexity in those messy equations we still have to deal with. Now, there are a bunch of different gauges you can pick, but there are two famous ones that do most of the heavy lifting. First, you've got the Coulomb gauge. This one is fantastic for situations where things aren't changing much. Static problems like fixed charges or a simple magnet. Then you have the Lorentz gauge. This is the absolute rock star for dynamic stuff, like light waves, because it plays really nicely with the relationship between space and time. That makes it totally compatible with Einstein's relativity, which is a huge deal. Let's actually see how this works. Say we pick the Coulomb gauge. That's the rule that says the divergence of A has to be 0. As soon as we plug that into our equations, poof, one of the ugliest, most complicated terms just disappears. And what we're left with is this much cleaner, much simpler thing called Poisson's equation. We've basically just turned a really hard problem into a standard textbook problem that people have known how to solve for ages. The Lorentz gauge? Oh, it does something even cooler. By choosing its special rule, we managed to completely decouple the potentials. Remember that big mathematical knot we started with where everything was tangled up? Well, this just unties it. We end up with two separate, beautifully simple wave equations. One for phi, one for A. And we can solve them totally independently of each other. That is a huge shortcut. Okay, so at this point, it would be easy to think that this is all just a clever math hack, right? A way to make the algebra less painful. But the truth is actually so much deeper than that. This freedom we found, it's not an accident. It's a direct echo of one of the most fundamental laws of the entire universe. I mean, that's the natural question, isn't it? Are we just playing games with symbols on a page here? Or does this gauge freedom thing actually mean something real, something deep about the cosmos? To get the answer, we have to look at one of the most sacred, unbreakable rules in all of physics, the conservation of electric charge. The fancy name for it is the continuity equation, but the idea is simple. It just says you can't create or destroy electric charge from nothing. If an amount of charge vanishes from over here, that exact same amount has to pop up somewhere else. It's always accounted for. And here it is. Here's the mind-blowing connection. When you actually work through the math, it turns out that the Lorentz gauge, that clever trick we use to make everything so simple, it only works if charge is conserved. The entire mathematical structure of gauge freedom rests on the physical reality of charge conservation. You can't have one without the other. They're locked together. So let's bring it all home. That hidden flexibility we talked about at the beginning, it's not a loophole. It's not a mistake in the laws of physics. It's a direct result of a much deeper law. Gauge freedom exists because the universe insists on conserving electric charge. The math has this wiggle room precisely because nature follows this fundamental rule. What started out looking like a clever shortcut to make our equations easier has led us straight to one of the most profound insights in all of science, that these mathematical symmetries and these physical conservation laws, they're just two different ways of saying the same thing. They're two sides of the same coin. And that is the deep, elegant language the universe is written in.